Hey students, thought I'd throw together a little quick video. There was a question thrown at me and it was more about part B than A, but just to make a complete video, let me kind of run through this. And also let me give you kind of the gist of it. This is from our chapter 3, and we're getting into our two-dimensional motion. And of course, this is kind of the educational approach of saying, hey, you got to be careful with direction and you have to do vectors. And so you have to treat X, separately from Y. That's why what I'm going to do here is, like all these problems, is I'm going to make myself a little chart and I'm going to look at, okay, what's happening in the X direction and what's happening in the Y direction. Okay, but let's just take a look at this problem. It says you fly 32.0 kilometers in a straight line in still air in a direction of 35 degrees south of west. Well, let me start by making a little compass rose here. Let's see, never eat soggy waffles. Okay, so here's my compass rose, and so we're going to go 32 kilometers, we're going to go in a straight line, and this is a key one, 35 degrees south of west. Okay, so west is over here to the left, and 35 degrees south of west means you move something like this, and so this would be a 35 degrees. So 35 degrees south of due west. Okay, find the distance you would have to fly straight south and then straight west to arrive at this same point. This determination is equivalent to finding the component displacements along the south and western direction. So, in other words, and maybe change a little color here, what we're trying to say and set you up for success in these next actually quite a few chapters, maybe next 7 chapters, is that when we have something like this, we can think of this motion, even though it's, one straight motion. You might say, oh, that's just one straight motion. We're trying to say it's the equivalent to going south and then going west. And so this one motion can be thought of 2 separate independent motions. And so these are referred to as the components. And of course, when we do our projectile motion and we have a grid and the thing moves, we can say, okay, when it moved somewhat in the X and somewhat in the Y. And even though it, anyways, it would have components. And that's what I meant on this chart here by saying, okay, you're going to see me do a lot of video solutions where I break it down and say, let's look at the motion in X and let's look at the motion in Y. And this is this first problem of the chapter, and it's setting you up for that little recipe here. Okay, so in a mathematical sense, let me change this to the Y-axis, and let me change this to the X-axis. And then I can do something like this. Now, I guess there's a couple ways we can look at this, and I'm going to put the 35 over here. Maybe I'll even do something like a standard triangle. Here's A, here's B, and the hypotenuse is C. There's hopefully a lot of things you remember from your math class, and this is a good time to review. For example, the sum of the square of the legs is equal to the square of the hypotenuse. So if we know the hypotenuse, which we do, it's 32 kilometers, and by itself we can't find the individual legs, but if we knew a B, then we could find an A, or if we knew an A, we could find a B. But there's other ways to get there too. This is from your algebra class. From your trig class, you could look at it this way. You could say, let's look at the, say, sine of 35 degrees. Sine means opposite over the hypotenuse. And that would be excellent right there, because this gives us a way to find A based upon the angle and C, which we know to be 32 kilometers. And then likewise, cosine of 35 is going to be a nice one also, because if you look at cosine of 35, Cosine means adjacent, so that would be B over the hypotenuse C. And again, we know the hypotenuse is the 32 kilometers, and we can use our calculator for cosine of 35 and get B. So these are the two we're going to use in order to find the value of A and B. Although, like I said, technically, once I got A, I could use this to get B, or I can get B and then use A. So there's a lot of ways to get B. And also, there's tangent of 35, which would be A over B. And so by itself, you can't do anything if you don't know A or B, but you could incorporate this with the other equations. So let me not worry about this or this for this particular equation. Let me just use the two trig functions, sine and cosine. And let me take this as an opportunity to say, keep in mind that if you ever want to find a distance that is opposite of the angle, so opposite of 35, use the sine. And if you ever want to find a distance that is adjacent to the 35, use the b. Okay, so now back to my page here where I made this little chart. I would do this. I would say for the x component, and so this is the b one here, I'm going to write cosine of 35 degrees equals b over c, and c is equal to 32. So rearranging this, I would say 32 times cosine of 35 degrees gives me the b component, which would be the westward component. So this would be 32 times cosine of 35. And so B has a distance of 26.2. And so coming back to the question, it says, determine the distance you fly. Determine the distance you would have to fly straight south. So that's not what I did yet. And then straight west. Okay, so this is west. So I would have to go 26.2 kilometers west. If we're talking about an x-axis, we might call a negative distance. But we don't, when you do a compass rose, we use east and west, not plus and minus. All right, so that's how far west. And then, of course, the y direction, this is what I call the A. I can get here from the sine. So let me do that one. Sine of 35 would equal to A over C. And again, the C, the hypotenuse, is 32. So rearranging this, I would say 32 multiplied by the sine of 35 degrees. Oh, you know what? I just better check my mode. Am I in degrees? Yes, I am. Okay, so I did this one right. I do a lot of problems and switching back, and sometimes I forget which mode my calculator's in. Let's see. So sine of 35 times 32 to get A, and then this would be A equals to 18 point, and I'll round it to a 4 kilometers. So I guess what we're saying here is if you go 18.4 south, turn the plane 90 degrees, and head west for 26.2 kilometers, you'll get to the same point as if you had gone 32 kilometers angled down or south of west by 35 degrees. And maybe just kind of a check, maybe I'll do the Pythagorean theorem here. If this is the A, I'll do the A squared, so 18.4 squared, plus the B squared, 26.2 squared. That should equal the C squared. So let me take the square root of that. Yep, and I get 32, other than some rounding. So perfect. So there's A, and then let's go to the question that was asked to me, and I think it had to do with this rotation of the axis. Watch this. B, find the distance you would have to fly find the distance you would have to fly first in a direction of 45 degrees south of west, and then in a direction 45 degrees west of north. these are the components of a displacement along a different, oh, I see. Okay, well, let me draw the picture here. Guess I kind of used up that page. Let me, right here on B, let me do another compass rose here. Okay, never eat soggy waffles. Okay, so I've got my grid. And so it says, find the distance you would have to fly first in a direction that is, okay. What am I, guess I'm trying to say? Maybe I should put, now it makes sense. That was a little hard for me to understand. Hopefully it wasn't for you. But it says find the distance you would have to fly first in this direction. So in other words, you're going to go to the same spot. All right, so let me just put ... here, same spot, okay, where we went 35 degrees, and then 35 degrees south of west. And if we actually flew this direction, we would have to go for 32 kilometers. Kilometers. Now, the problem we just did in A is saying this, that you could get to the same point by first going due south, which we just figured out to be 18.4 kilometers, and then due west by 26.2 kilometers. But this problem is trying to say there's other ways you could get there. And let's see, I used blue and red. How about I switch over now to green? Let's see if my green's working. Yeah. I don't know how well the green's going to stand out on the yellow. It looks pretty decent here on the camera, so I think you can see it. But it says, find the distances you would have to fly first in a 45 degrees south of west. So in other words, you first go this way. And let me just maybe put a dotted line. Then, so that's south of west. And then in a direction that is 45 degrees west of north. So west of north is off at this angle. So in other words, when you got to right here, you would have to make your turn and go here. So what this problem is trying to say here is you could still get to that same point. You don't have to do the blue one, which is straight there, 32 kilometers. You also don't have to do the red one, which is 18.4 south and 26.2 west. What you could do, and shown here in the green, is go south of west and then turn and go west of north. And so this would be some distance, and this would be some distance. And that's what they're trying to say. And now I understand why the student asked this question, because, you know, I had to think about it too. What are they trying to say? Find the distance. Yeah, so they're trying to say, find the distance you would have to fly if you first went along this green path, then you turn, find this distance. And so you don't confuse it, why don't I just say, instead of me calling it A and B this time, I'll still call the hypotenuse C, but I'm looking at this right triangle. Why don't I call it D and E? So using a kind of Pythagorean theorem here, I would say a D squared plus an E squared is equal to the C squared, where again the C is that 32 squared. And I think that's why then the author says, in kind of a side note here, saying these would be the components of a different set of axes, one that has been rotated 45 degrees. In other words, if I had a grid of X and Y that was twisted. And what they're trying to do is set you up, because in about 2 chapters, so let's see, this is chapter 3, so in chapter 5, and maybe even early as chapter 4, we'll do this. We will take our traditional grid and we will rotate it. And granted, rotating it is a little harder because it's not very common, but it'll have a lot of advantages and it'll be worth the hassle of twisting it. So now that I think about what the author's doing here, I really like that. That's a good thing for him to help kind of set you up here with. Okay, now let's actually solve it. Now, maybe I will, I'll stay with green here for a little bit, even if it's kind of hard to see. But I want you to see here then that I have this little triangle here. And I'm trying to find this adjacent piece to say maybe this angle right here, the D and the E. And so I'm going to make a little mark here. And it's kind of small there, so I'll just point to it and say, well, what is that little angle? So remember, we are kind of rotating this grid to south of west. That's 45 degrees. And then this angle is 35 degrees. So that means this little angle in there must be 10 degrees. And that's what I want to comment on. There is just a small little angle here of 10 degrees. And that's the triangle I'm going to look at. So I'm going to look at this triangle. But I'm going to get myself a new piece of paper here. Maybe I'll call it page 2 and page 1. Page 0. Anyways, back here. So looking now just at this triangle and noting that this angle is now 10 degrees, I could then say cosine of 10 degrees is the adjacent, that's the D, over the hypotenuse, which is the C, and that's the 32. And so if I bring the 32, I get 32 times cosine of 10 degrees equals the D. Now let me just pause there. I hope that looks a lot like what we did in part A here, where we took 32 times cosine of this angle. This was the angle between a straight line there and the x-axis. And that's really what I have here. The 10 degrees is the angle between the straight line there and the x-axis, see? And so thinking of our grid as being rotated 45 degrees, we've got this 10 degrees here, and so that's why we're doing cosine of 10 degrees. So if the plane flew along this path, the D would be the 32 times cosine of 10 degrees, would have to fly 31.5 kilometers. And so that might be my x-axis in this rotated grid. And then after the plane gets to here, they make a turn, they would do this E part. Now notice this E is opposite of this small angle, which is 10 degrees. So that would be sine of 10 degrees. So the sine of 10 degrees would be E over C. And again, remember, the C is 32. So this would be 32 times the sine of 10 degrees is equal to E. And then E is not going to be too much of a distance, 32, because sine of 10 is pretty small. And so I'll call it 5.6 kilometers, 5.6 kilometers. And so there's our two distances. So again, just to make sense out of this, hopefully you see that the pilot has a bunch of options of how to get there. The straight line shot is the 32 kilometers. The south and then west is the 18.4 south, and then the 26.2 west. But this last one is giving us another option where we can fly south of west for 31.5 kilometers and then turn and go west of north for 5.6 kilometers. All right. Hope that helped. Bye now.